Okay. So, we meet again to continue our discussion on linear first order autonomous systems. We will take an example from process industries today and see how we can actually use these concepts for understanding process industry and allied systems. So, before we go into the details, let us have a very quick recapitulation of what we learned from the first lecture till the third lecture. We were interested in understanding the dynamics of first order linear autonomous systems. So, the definition of first order was that they are the systems in which there is one and only one governing dynamical equation, and the equation is of first order and the equation is going to be an ordinary differential equation. The system was defined as linear if the corresponding operator was a linear operator, and the condition for linearity was that it has to satisfy two properties. If u and v are the vectors in the linear vector space for which the operator was defined, then according to the first property, L operating on u plus v should be equal to L operating on u plus L operating on v. And if alpha is a member of the field over which the linear vector space is defined, then L operating on alpha times u should be equal to alpha times L operating on u. These are the two conditions which must be satisfied for a system to be linear. It is important to note that the solution functions themselves do not need to be linear, which means that the solutions can be sinusoidal, the solutions can be exponential, or it can be any nonlinear function, but the corresponding operator which governs the dynamics of the system must be a linear operator. Finally, we learnt about the definition of autonomous system. So, if you have a linear first order ODE and you are in a position to rearrange the ODE such that dx by dt is given by some function of x and t, then the system would be called autonomous if and only if the right hand side f is going to be only a function of x, which means if you can express the system as dx by dt is equal to f of x such that f is not an explicit function of time, then the system is called autonomous. Now, all of these concepts can be applied to examples which come from process industries, and we are going to take one such example. So, let us look into the example today. What we have in front of us is the schematic for the system. We have a solid body which is maintained at a temperature T 0. Okay. So, the solid body has a temperature T 0 and the body is dropped in a reservoir which has a temperature of T infinity. So, liquid reservoir which is at a temperature T infinity. Reservoir by definition means that the temperature of the reservoir is not going to change, which means T infinity is going to be a constant. In our entire analysis, T infinity is going to be considered a constant. So, now when you drop a body which is at temperature of T 0 into a liquid which is at a temperature of T infinity such that T infinity is never going to change, then what is going to happen to this system physically? What is going to happen is that the temperature T, which is the instantaneous temperature of the body is going to change, right. So, the instantaneous temperature of the body is going to change, and what is the governing equation that it would follow? The governing equation can be determined quite simply using energy balance. So, the governing equation is in front of you, where dT by dt, the time rate of change of temperature of the body at any instant of time. So, T is the instantaneous temperature of the solid body, is given as minus h times A s divided by rho V c times T minus T infinity. And it is not very difficult to see how this equation comes. So, you have d T by d T multiplied by rho V c, which is nothing but d by dt of m c p T, which is the energy content of the body. So, the rate at which the energy content of the body changes should be equal to the heat transfer to the reservoir from the reservoir, depending upon the temperature of the reservoir and the temperature of the body. So, you equate these two terms and get this model equation. Okay. So, H is the heat transfer coefficient, A s is the surface area of the body, rho is the density of the body, V is the volume of the body, C is the specific heat of the body, and it is important to know that T is the instantaneous temperature. So, the dynamical variable of interest in our case is T. So, T is a function of small t, which is time. Okay. So, now let us see what all can we analyze in this case. The first question which we need to address is that what is or are the equilibrium solutions of the system. Okay. So, let us look into the model equation. The model equation is d T by d T is equal to minus H A s upon rho V c multiplied by T minus T infinity. Okay. Now, what I see is that under certain approximations, H surface area of the body, rho, V, C, they all can be considered constants. I am saying that under certain approximations, because over a very wide range of temperatures the specific heat of the body may change and so on, and this is true for all of the properties which have been mentioned here. But if we assume that all of these properties remain constant over a temperature range for which we are doing our analysis, then what I see is that H A s upon rho V c can be simply substituted by a constant, and let us say that constant is A. Let us say that the constant which gives this multiplication and division is simply A. So, if I know the relationship between these constants and A, then I can say that fine, for example, if heat transfer coefficient increases, the value of my constant A will increase. If the density increases, the value of my constant A will decrease, and so on. So, therefore, for the sake of mathematical convenience, I will replace these constants with a simple constant A, making my model equation d T by d T is equal to minus A times T minus T infinity. Okay. This has been done just for the sake of mathematical ease. Okay. It is not going to change any of our results. So, my first question is what is or are the equilibrium solution or solutions of the system. In our previous case, we saw that dx by dt is equal to f of x. If this is the dynamical equation, then if I equate it with 0, then I get the equilibrium solutions x e as the solution of f of x is equal to 0. So, therefore, in this case I can write minus of A t minus t infinity is equal to 0, which gives me t equilibrium as t infinity. Now, does this make sense? So, let us analyze what is going on. You have a body and you have dropped that body in the reservoir. The reservoir temperature is maintained constant and you allow the temperature of the body to change. Okay. So, the temperature of the body changes from T 0, which is the initial temperature of the body, to some temperature, right. So, when equilibration takes place, which means nothing will further change with time and T infinity remains constant, the only way that the gradients in the system would vanish is when your T becomes T infinity. This is quite a trivial physics which can be extracted out of this analysis, and this analysis seems to be consistent with what we know either from training or from experience. So, therefore, our equilibrium solution is that T equilibrium is equal to T infinity. Okay. So, now what we need to do is we need to solve the model equation analytically, to determine the time evolution. How can we know the time evolution of the system, and then correspondingly develop the phase portrait for the system. So, let us see how this can be done. So, our model equation, let us write the model equation. Our model equation was dt by dt is equal to minus a t minus t infinity. Okay. This is our model equation, and the initial condition which has been given to us is T 0 is equal to T subscript 0. This is the initial condition which has been given to us. Now, to solve equation 1, what I will do is I will introduce a new variable and I will say that T star is equal to T minus T infinity. Okay. So, let us say that I have a new variable T star which is equal to T minus T infinity, and since T infinity is a constant, I can write dt star is equal to dt. Okay. So, from equations 2 and 3 and substituting them in equation 1, what I get is d t star by dt is equal to minus a t star. And does this equation look familiar? Indeed, because in our previous lecture what we saw was that we had the equation dx by dt is equal to ax, right. So, it is basically the same equation, which means that the entire analysis that we did in our previous lecture holds true for this system as well. In fact, that is the basic motivation behind introduction of any mathematical technique. So, that if you understand the technique well, you can then use that technique for a series of different situations. The current situation being the analysis of dynamics of change of temperature of a body, but if analogous equations arise in other situations as well, the overall dynamics, the features of the dynamics will remain the same. So, let us see how we can solve the equation. As we solved yesterday, we will have T star which is equal to a constant C, integration constant times e to the power minus a t. Okay. And I need to determine the integration constant, that can be done with the help of the initial condition. So, let me plug in the original definition of T star. From equation 2, my T star was T minus T infinity, and this is equal to C e to the power a t, and at t is equal to 0, my temperature T is equal to T 0, right. So, I will substitute it in equation number 7. So, I have T 0 minus T infinity is equal to C. Okay. In other words, I have T minus T infinity is equal to T 0 minus T infinity times e to the power a t, or finally, I can write my time evolution. So, let me make it explicit that t is a function of small t as T infinity plus T 0 minus T infinity e to the power, it has to be minus, and this also has to be minus. So, minus a t. Okay. So, the exponential has minus of a t. So, this is my final solution to the model equation. Okay. And this now puts me in a position to draw the phase portraits for the system. Okay. So, let us see if we can draw the phase portraits for this particular system. So, my equation is T of small t is equal to T infinity plus T 0 minus T infinity e to the power a t. So, the model equation is T of t is equal to T infinity plus T 0 minus T infinity e to the power minus a t. Okay. So, how can I draw the phase portrait for the system using this model equation? Now, as I see that, so let me draw the coordinates first. This is going to be time, this is going to be temperature. Okay. So, my initial temperature is T 0, okay. So, T 0, and my equilibrium temperature is T infinity, which means that I am going to start my system with temperature is equal to T 0, and it should ultimately end up at T infinity. So, as time t tends to infinity, my temperature capital T should tend to T infinity. Okay. So, let me have an condition, an initial condition which is given as T 0. So, this is the initial condition of the system, and finally, the system has to reach the temperature T infinity, okay, assuming T infinity to be greater than T 0. So, you have a water bath which is maintained at say 70 degree centigrade, and then you drop the sphere or a body from the top at room temperature, right. So, this is the typical condition which it would satisfy. So, let me make a dotted line and another dotted line. Okay. So, as the temperature reaches T infinity, the gradients would become 0, and the initial condition is T 0. So, therefore, your entire system would be confined within these two limits. You will have T infinity at the top and T 0 at the bottom. Okay. So, now how would you draw lines which correspond to this equation such that the bottom is T 0 and the top is T infinity? You see the function here. This is an exponential function, an exponentially decaying function in fact. So, what is going to happen? You will start with T 0 and your ultimate value T infinity is reached by multiplication of T minus T infinity by an exponentially decaying function. This is how we understand the equation. Well, you can understand the equation in other terms. You start with T infinity and then you keep on adding the difference, but the difference itself keeps on reducing exponentially with time. So, therefore, the way you can look at this is that as at long time intervals the system is coming here asymptotically, and then it has to start from here. So, the way we can join these two is like this. This is one of the phase lines. As I change A, what can happen is, if you start with the same initial condition depending upon the system properties, you may reach quickly or you may reach slowly, but asymptotically what is going to happen is that you are going to reach temperature T is equal to T infinity. Okay. So, what do we understand from this solution is that if you have T given as T infinity plus T 0 minus T infinity e to the power a t, the exponential part of your function will give the curve to the system. What is the importance of this parameter a? If a is large, the change will be faster. Okay. So, therefore, if I have a 1, a 2, a 3, then I can write a 1 to be greater than a 2 to be greater than a 3 in magnitude. Okay. So, this is the phase portrait for the system, but this corresponded to a situation where T infinity was greater than T 0, which means that you dropped your body in the oil bath or a reservoir, which was at a temperature which was greater than the initial temperature of your body. Let us see if we can do this in a reverse manner. So, our new situation is like this, that you have T 0 is equal to T subscript 0, T equilibrium is equal to T infinity, and now T 0 is greater than T infinity. Okay. T 0 is greater than T infinity. So, again I will draw the axis, this is time, this is temperature. Okay. Again, my system has two extremities, one extremity is T 0, the other extremity is T infinity. In the previous case, T infinity was larger, T 0 was smaller. Now, I have reversed the situation, T infinity is now small and T 0 is large, which means that say you have a hot plate, a hot steel plate, and you quench it in an oil bath to reduce its temperature quickly. That is what you want to do. That is a metallurgical operation which is done. So, in this case again I have two extremities. So, let me say that I have T 0 here and I have T infinity here, and these are the extremities. So, all of my phase lines will lie between these two extremities only. Okay. Fine. And then what I see is that since T E is T infinity. So, this is my equilibrium temperature, this is my equilibrium solution rather. So, as T tends to infinity I should reach here. So, asymptotically I should have this solution. Okay. So, how do I start from here and reach here, taking into account the exponential decay which is associated with my model equation. Okay. So, if we remember, our model equation was T of t is equal to T infinity plus T 0 minus T infinity e to the power minus a t, okay, e to the power minus a t. So, what do? I start with T 0, and because of this exponential decay, the typical behavior of an exponential decay, f of x versus x is this, right, and then this would be augmented with T infinity and T 0 minus T infinity. So, the way the phase line would look like is this. This is one of the phase lines. I can have same starting initial point and different phase lines, all of them would asymptotically go to T infinity and so on, and if this is A 1, this is A 2 and this is A 3, 3 different values for A, then as I said, the magnitude of A will give the quickness of the system to adjust to the new condition, and therefore, in this I can write A 3 to be greater than A 2 to be greater than A 1, fine. So, and all of these A's are functions of heat transfer coefficient, surface area, rho, V, C and so on. So, now you can adjust the values of A, AS, H, rho, CV and so on to get the value of A, different values of A 1, A 2, A 3 and so on, and then you can determine how quickly or slowly will your system reach the equilibrium state, or it would go to T infinity. These are the different solutions. Now, what I can do is I can make another set of phase portraits to give you an idea about the solution or the solution behavior. So, I can superimpose both of them. I have T here, I have T here. So, if this is my T infinity, then when T 0, is less than T infinity, what is going to happen? I am going to rise exponentially, I am going to rise like this, not exponentially, I am going to rise like this, and therefore, for different T i's, T 0 1, T 0 2 and so on, my phase lines would look like this. And when T 0 is greater than T 0 is greater than T infinity, then what I will see is that I will see exponential decay like this, and all of them would go asymptotically to T infinity, right. But now, what I see is that this is true when A is greater than 0, because your equation was T is equal to T infinity plus T 0 minus T infinity e to the power minus a t, right. This is true only for A greater than 0, and A in fact was H times A s divided by rho V c, right. Now, all of these quantities, heat transfer coefficient, surface area, rho which is the density, volume, specific heat, they are all greater than 0, which means A would always be greater than 0, right. A would always be greater than 0. Had it not been the case, then how would the phase portrait have looked like? Now, physically this is not correct, let me emphasize this, but for the sake of mathematical completeness, if you want to draw the exact same system for a less than 0, then how would the system look like? Well, you will have again the same equilibrium solution T infinity. So, if you start with T 0 1, start with T 0 1, what is going to happen? You will not reach here, in fact, you will go down, and for T 0 2, which is greater than T infinity, you would rise here. Now, this looks a little weird, but this is in fact not mathematically inconsistent, because what then you will need to do is you will need to go. So, let me draw it again. Now, I have considered negative time as well. Okay. So, this is the temperature, I have considered the negative time as well. So, A is in fact greater than 0. How the solutions would look like? You start with this, and this is going to be a solution. So, you start with T 0 here, okay. You diverge, and similarly you go here, this is T 0 2, right, and this would be your T infinity. Okay. So, you will need to shift the axis such, so this is not 0. So, this point is not 0, this is not 0, this is T infinity. You can draw the x axis like this. So, this is T. Okay. So, now what do we see here? What we have seen here is that for a less than for a, so this has to be a less than 0. There is a correction there, a has to be less than 0. So, mathematically if there is a condition such that for the model equation T is equal to T infinity plus T 0 minus T infinity e to the power minus a t, such that a is less than 0, making the exponential positive, this will be the phase portrait. Physically, for the current situation, this phase portrait will not hold true, but you may tomorrow come across some other situation, some other system for which you may get similar analysis, and then you may be ready to understand that the solution behavior would look like this. And therefore, what you see is that there is a divergence. So, the system is unstable, this line, this equilibrium solution is unstable. Whereas, for the current system, when you drew the phase portrait like this, this is the equilibrium solution, temperature, time, the equilibrium solution is like this, or it looks like this, T equilibrium, you will see that T equilibrium is stable. In fact, what I can do is I can make this particular portrait also mathematically complete. We have considered time only positive, what you can do is time, temperature, everything for the sake of mathematical completeness negative. So, what is going to happen is you can draw phase lines like this. These would be the phase lines, and all of them would asymptotically reach T equilibrium is equal to T infinity as time t tends to infinity. So, we would stop here and continue the discussion on this particular topic and see whether we can actually see these details using an alternative method. Thank you.